Good day, ladies and gentlemen. You are welcome to our lecture number 4 on Cmen843. Today we are going to look at what we call defects, intrinsic defect in semiconductors. As you all know, the electronic materials that are used, they are called solid state electronics because they are in a solid state. And we also have seen that we have elemental like silicon, like germanium, and we have compound solid state semiconductors. So the defect is nothing but whenever there is irregularities or improper arrangements of molecules in any of the semiconductor materials that is being used. So whenever the temperature is not at absolute zero temperature, that is 0 degrees Kelvin, definitely the crystals, that's the arrangement of the molecules in the semiconductor materials like silicon, they will never be 100% perfect. So what we call intrinsic lattice defects is any defects, any misalignments in any of the semiconductor material that is being used. And as we have highlighted here, it means whenever the temperature is at that absolute zero, there is tendency the molecules will be in proper arrangement. So whenever the temperature is more than that, we get some defects. Okay, so it means temperature or heat is one of the factors that causes defect in semiconductors. And these defects, they are categorized into different types depending on the nature of the defect. For instance, we have what we call point defects, we have line defects, we have plane defects, and of course we have spatial defects, and sometimes we call it volume defects. So whenever you have a foreign material, that is anything that is not in that is not pure of that material. For instance, if we are dealing with silicon, whenever you have any element that is not silicon found in the body of that silicon, we call it a foreign species. So whenever they are in a crystal of a semiconductor, they cause what we call the foreign defects. But the one we started talking about is intrinsic, that is the defects from the arrangement of the molecules of that atom or element itself. And as we have seen, we said we have different types: point, line, and what have you. So let us look at them one after the other. First of all, what is a point defect? This point defect is the simplest kind of defect that can exist in any crystalline lattice of a semiconductor material like silicon. And it is categorized into two also. But the one that is most elementary, the most common, is what we call the vacancy point defects. And sometimes we call it Schottky defects. And this is nothing but a hypothetical process in which a molecule or an atom is removed from the interior of the silicon or germanium and transferred to the surface of that semiconductor material. So whenever that happens, we said we have a point defect, and this point defect, as I have said, is called vacancy. Okay, that is where we're supposed to have all the atoms or all the elements present in the interior of the semiconductor material, but we have a situation where one or more than one of the atoms is taken from that interior part where it's supposed to be to the surface. So we call that vacancy, and sometimes we also call it a Schottky defect. Now, if you want to form this vacancy, that is to remove an atom or element, a molecule from the interior of semiconductor material and transport it to the surface, it requires an energy. We have to input an energy into the silicon lattice, and this energy required is approximately 2.3 electron volts. In terms of this semiconductor materials, 2.3 electron volt is a big energy. But if you look at it as a general term, a 1 electron volt is the same thing or is equal to 1.6 times 10 to the power minus 19 joule, which is very, very small. But in this case, it is significant. So whenever the temperature is at around 300 degree Kelvin, that is around room temperature, we have what we call thermal fluctuations. And these thermal fluctuations, they can produce very small concentration of these vacancies. That is, the thermal fluctuations will be able to remove very few of molecules from the interior of the silicon lattice to the surface. And the second type of this point defect, we call it interstitial. Interstitial is the one that is like inverse to the vacancy, because if you can remember, I said vacancy is a hypothetical situation where an interior molecule or atom is removed to the surface of the silicon lattice. But this one is assumed that we take an element, or we take an atom or molecule from the surface of a semiconductor material like silicon, and we transport it into the interior of that same silicon lattice. And the formation of this interstitial defect requires larger amount of energy. That is, the amount of energy required to remove an atom from the interior to the surface is smaller than the one required to move an atom from the surface to the interior. And for this reason, this interstitial defect is very, very rare. It doesn't happen so often like the vacancy because of the requirement of this large amount of energy. And for us to really understand what we have been discussing, we have two diagrams here, A and B. If you look at A, it is showing, the arrow is pointing that an element, an atom or a molecule is taken from the interior of the silicon and transported to the surface. While the second one, the B, is showing a situation where we take an atom from the surface and we transport it into the interior of that lattice of a silicon or germanium, depending on the situation. So this formation of the vacancy, we said, is what? Transfer of an atom from the interior to the surface. So whenever you want to create a single vacancy, you have to break 4 bonds. Because if you look at diagram A, the point where this atom is removed, you can see that it is surrounded by 4 neighboring atoms. So you need to break 4 bonds before you can form a single vacancy. But if you want to form 2, that is di, 1 and 2, which are neighboring to one another, if you want to transfer them from the interior to the surface, this time around you don't need to break up to 8 bonds. You require breakage of only 6 bonds. Therefore, it is in most cases the di vacancy is formed more often than forming the single vacancy, because that one requires 4 and this one requires only from the surface to the interior of the silicon. To form the interstitial is very, very much difficult, unlike the di vacancy, which is more frequent than mono or single vacancy. Because we have already said that formation of the interstitial single one is very difficult, so to form the di is more difficult. So now these are the 2 types of the point defects, the vacancy and interstitial. The next one is line defect, and this line defect is nothing but or sometimes it is called dislocation. And it is also of two types. We have what we call edge and we have what we call screw. And this edge line defects and the screw line defects are illustrated in the diagrams here for simpler or easier understanding. If you look at the A, you can see that it's like I have planes from the top downward to the bottom, which are divided into two by a horizontal line. So you can see that looking from the extreme left, you can see that we have the upper and the lower planes, until when you come to the one on the right hand side, you can see that we have the bottom plane, but the top one is not in existence. So if you look at this, it's like we shift the the upper part of the atom molecules in such a way that a vacancy is left at the bottom, as you can see from this figure A. But if you look at the figure B, the defect is not like forming lower plane and leaving the upper plane, but this time around it's like pushing the complete part in such a way that it is now moving in a wind or in a cycle, just like a spring. So an ideal edge dislocation is considered to be as a result of insertion of extraneous half plane of atoms. Let me go back to the diagram. You can see that this lower plane, which doesn't have the top one, we assume that this defect is created by introducing this lower or half plates at the bottom, whereas we don't have corresponding at the top. So there must be a localized increase in the strain energy if you want to create that, because for you to move an entire plane, either the lower plane or the top plane, you have to apply a kind of an amount of energy. And the other one, as I said, we call it the screw because it is in the winding part, just like a screw. And for this pure screw dislocation to happen, we don't need any extraneous plane of atom to be inserted. However, the atomic planes within the lattice, they are supposed to be displaced in the arrangement in such a way that they will now be winding just like a staircase of a spiral spring. So therefore, these images show the two types of the line defects. The first one is what we call the edge, and the second one is what we call the screw line defects. Now, the next one is what they call a plane defect, and this plane defect happens in a situation where we have part of a plane is completely omitted. That is, arrangement of some atoms within the molecules or within the lattice structure of a silicon or germanium is completely missing. And if you look at this, the A diagram, you can see that starting from the left, I have my vertical line, all the atoms are there. The next one also, all the atoms are there, though they have moved in a random order. The next one also, but if you look at the line number 4, either from left or from the right, you can see that part of the atoms is missing. Therefore, this plane is completely omitted from the structure, and for this we call it a plane defect because part of the atomic plane is missing. It is supposed to be a straight line from top to the bottom, but you can see in the middle it has a part of it has been removed, and this is the reason why these closed ones to it are bending toward that position, tending to fill the vacancy, and this is what we call the plane defect. But if you look at this, is what we call the intrinsic because it is part that has been taken away from the body of the lattice structure. But if you look at the B1, you can see that all my lines, if you start either from left or right, 1 2 3 4, and also from left 1 2 3 4, all of them are there. But in the middle you can see that another plane, half of a plane, is inserted. We assume it has been taken from elsewhere and it has been inserted into the middle. And for this we call this one, we call it extrinsic stacking, because we assume plane of an atom is inserted. But the first one we call it extrinsic because something has been taken away from the interior to the outside of the structure. Now the last one, as we have said, we have point, we have line, we have plane, and the last one is what we call the spatial defect. And sometimes this spatial defect we call it volume defect. And this kind of defect is formed whenever we have concentration of the other defect of lower dimensionality. That is, wherever you have repetition of point defect or line defect, or a plane defect, you can come to creation of what we call a spatial or volume defect. For example, whenever you have so many vacancies which are coalesced, what we mean by coalesced, they are next to one another, they can form what we call a bulk void. And these bulk voids can be categorized as type of what? A spatial defect or volume defect. And of course, these defects, either point or line or plane, whenever its density become large, it means the complete structure of the silicon has been, disorganized, and this causes a higher order defect, which is the spatial or volumetric defect. And of course, any material that experience so many defects at different places, it will now become what we call an amorphous. An amorphous is nothing but something that doesn't have a regular order or a proper arrangement. So any significant quantity of these dislocations or the stacking fault or the bulk defect, you find that they are electrically not functioning the way they are supposed to perform. Therefore the performance is very poor.
Okay, so now we are going to look at the relationship between this defect we have discussed and the thermodynamics. If you can remember, we have explained that the defects actually don't happen at absolute zero temperature, that is 0 degree Kelvin, but whenever there is rise in temperature to around room temperature, 25 degrees Celsius or around 300 degree Kelvin, there are some defects. So these defects are caused, as we have seen, by the random motion of atoms in the lattice itself whenever there is a thermal increase. And of course, at room temperature, this thermal energy is very small, but it is not zero. But nevertheless, it is less than the binding energy of the lattice structure of the semiconductor material. So therefore, because it is not up to the amount of the binding energy, we have very little number of defects in the lattice structure of silicon or germanium. But nevertheless, since the temperature is not 0 degree Kelvin, we have some. Therefore, the defect is not going to be 0. So for this reason, whenever there is rise in temperature, there is spontaneous defect generation. That is random or natural defect generation, which can be described by the principles of thermodynamics. And for us to be able to do this, we have some 4 classical parameters of thermodynamics, and which are also sometimes called the state functions. And these 4 parameters are: number 1 is A, which stands for the potential energies. E stand for the internal energy, G stand for the enthalpy, and the H stand for the free energy. The A and the G, sometimes we call them Helmholtz free energy and Gibbs free energy respectively. That is, A is the Helmholtz free energy and G is the Gibbs free energy. The E and A, we use them in a situation where we have constant volume thermodynamics. Remember our gas laws, we have Charles' law and we have Boyle's law. One of them deals with the constant pressure and the other one deals with the constant volume. So in a situation where the volume is constant, we use this E and A. And on the other hand, when we have constant pressure thermodynamics, the A and G are the ones that are applicable. And this distinction between constant volume and constant pressure, it is not significant whenever we are concerned with those molecules or those systems where we have condensed phases. By condensed phases, we mean something like a crystalline solid where the molecules are actually very, very close to one another and they are fixed, they cannot change their neighbors. So in this case, this distinction between constant volume and constant pressure is not that very important. And however, the E and H, we consider them as identical as long as A and G are also identical. That is in a situation like that of crystalline solid I have just explained. Now, in addition, we have two additional thermodynamic parameters, and these are what we call the absolute temperature or thermodynamic temperature, represented by letter T, and we have enthalpy, which is represented by letter S. And we need to remember our fundamentals of thermodynamics, or even from our basic chemistry at secondary school level. Entropy is defined as the level of randomness or the level of disorder of a particular physical system. So the internal energy we talked about is the total binding energy of the crystal, and the free energy is defined as the amount of energy that is available to do work. And of course, the product of the temperature T and the entropy S, they are related to the internal energy and the free energy given by this relation. That is, A is equal to E minus Ts, where, as we have seen, E is defined as the free energy, and A, from here, we define it as potential energy. So the potential energy is equal to this free energy minus Ts, where T is the temperature and S is the entropy of the system. Now, we can also do our analysis if we consider relative values of these 4 parameters or 6 parameters in addition to the T and S. If we assume delta E stand for a given value change in the value of E, delta H the same thing, all these delta stand for changes in those parameters. Now our equation here, where we have A equal to E minus Ts, we can rewrite it as delta A is equal to delta E minus delta Ts. And if we are talking of generation of some vacancies, you know, the vacancy is one type of the what? Point defects. So if we want to generate an n number of vacancies in atomic lattice of a semiconductor, and we assume m is the number of vacancies in unit volume, that is per unit volume. So this m is now a function of n, which is the number of atomic lattice sites, and T, the temperature. So if we assume delta EV stand for the energy formation of a single vacancy, which is approximately 2.3 electron volts, as we have seen previously, then the free energy change, that is delta, that free energy for generation m vacancies is given by this formula, that is delta A subscript mv. This mv stands for m number of vacancies, is equal to m delta EV, where V is the number of vacancies also, minus T delta S mv, that is M is the number of what? Vacancy, and V stand for the vacancy. So if we look at this relation, it's actually the same thing as this, only that we added somewhat subscript. And instead of using E here, because the E we use here, we assume it's only one vacancy that is created. So this M came into being because we assume, or we are dealing with what? M number of vacancies per unit volume. Now, this delta A mv stand for the free energy for the formation of m number of vacancies, and delta S mv is the entropy for generation of m number of vacancies, and this entropy can be divided into two parts. That is, instead of using SMV, we can use SMV to power O superscript C and SMV superscript X. The one carrying C stands for the configurational entropy. That is the entropy randomness that has to do with the configuration, the number or the arrangement of the molecules. And this X stands for the XX entropy. As we said, the one that carry superscript C, we call it entropy associated with configurational entropy. So it is an entropy due to increase in what? Disorderliness associated with introduction of M vacancies into perfect crystalline structure. And the one that carry X, we said, is excess. What we mean by excess is that amount of random vacancies M generated. Now, if you want to find the configuration of vacancy or entropy, that is the one that carries superscript C, we can use Boltzmann relation that defines entropy as this: S is equal to K ln W, where our S is our entropy, K is proportionality constant, we call it Boltzmann's constant, and W is the number of, the amount of energy required for creating that M number of vacancies. And if you want to calculate this W, we use this binomial function, which says W subscript MV is equal to n factorial all over n minus m factorial, then m factorial. So from here, we can also find the expression for m if we consider what we call the condition for equilibrium. The condition for equilibrium is given by ln of m all over n minus m, which is equal to minus delta EV all over KT, where m is the m number of vacancies and n is the number of sites per unit volume, as we have seen previously. And E, we have seen it is the free energy for number of vacancies V, K is Boltzmann's constant, and T is the absolute temperature in Kelvin. Now, in order to find the simplified expression for M, which is the number of vacancy, we will make one assumption to say that here we have n minus m. We make assumption that this n is much bigger than m. which means I can neglect this m. So I have ln of m all over n equal to this much. Now, if you want to remove this ln, you take the exponential of both sides, and doing that will give you m over n, which is equal to exponential everything here. Now you multiply both sides by n, you will be left with m equal to n exponential minus delta ev all over kt. And where m we said is the number of vacancies we want to create per unit volume of a crystalline structure. So, ladies and gentlemen, this is the end of our lecture number 4. And as every day, I will continue to suggest that for you to actually understand this thing we are discussing clearly, you need to download the video, you watch it some number of times so that everything will be clear to you. In case you still have some problems, you are free to contact me. We can discuss and I can give you any possible explanation. Thank you very much.